What are the odds that two stars would explode into naked eye visibility? Two massive earthquakes would tear through Venezuelan bedrock, and an infamous interstellar atlas would get sideswiped by a solar storm, all within 72 hours. If this was a movie script, editors would reject it as too coincidental to believe. But this is our story, and what happened in late September 2025 delivered the most synchronized cosmic performance in modern astronomical history. Picture yourself standing outside on a clear September night. Above you, stars that have been invisible for years suddenly blaze bright enough to see without telescopes. Beneath your feet, the solid ground that feels so permanent is actually floating on a churning sea of molten rock, occasionally reminding us it's very much alive. And threading through the space between planets, an object that traveled millions of years from another star system is passing through a cosmic storm launched by our own sun. These things happen all the time, sure. Stars explode, earthquakes shake the ground, the sun throws tantrums, comets and asteroids drift through our neighborhood, but they happen on different timescales, in different places, affecting different parts of our universe. What made this week genuinely strange was the compression, the way everything seemed to happen at once, as if someone had taken the normally slow, stately rhythm of cosmic events and cranked up the tempo to breakneck speed. On September 23rd, astronomers detected V1935 Centauri, a nova that erupted in the southern constellation Centaurus, brightening to magnitude 5.8. That's just barely visible to sharp eyes under dark skies. Within days, another stellar explosion announced itself. V7994 Sagittarius blazed forth in the Archer constellation at magnitude 6.2. Two stars, both suddenly visible to anyone willing to step outside and look up. Meanwhile, 7,000 miles away from the nearest observatory, Earth itself was making headlines. At 22:21 Coordinated Universal Time on September 24th, a magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mena Grande in Venezuela's Zulia state. The tremor originated just 7.8 kilometers below the surface, sending shockwaves across both Venezuela and Colombia. But nature wasn't finished. Hours later, at 03:51 on September 25th, a second quake, magnitude 6.3, ruptured the same region. Twin stars, twin quakes. And overhead, invisible to naked eyes but tracked by satellites, something else was unfolding. Solar weather forecasters were monitoring coronal mass ejections, billion-ton clouds of magnetized plasma hurled from the sun at speeds exceeding 1,000,000 miles per hour. Their computer models suggested these solar storms were crossing paths with something unprecedented. 3I Atlas, the third, confirmed interstellar visitor to wander through our solar system. Here's where the timeline becomes almost theatrical in its synchronicity. The nova discoveries and Venezuelan earthquakes clustered around September 23rd through 25th. Coronal mass ejection forecast models showed peak activity during the same window. And 3I Atlas, discovered just 2 months earlier, was navigating the inner solar system during what may be the most active period of solar cycle 25. We're not claiming a causal chain here. That would be premature, possibly reckless. What we're doing is mapping the cluster, documenting the convergence, and preparing to weigh mainstream scientific explanations against more adventurous hypotheses. After what just happened, even the most rational minds are starting to wonder if we're witnessing something far stranger than chance. Tonight, we'll dissect each event with surgical precision, examine the science behind stellar tantrums and planetary convulsions, then venture into the uncomfortable territory where coincidence meets pattern recognition. Stay with me, because what we discover about September 2025 might challenge everything we thought we knew about what's really happening up there. In the pre-dawn hours of September 23rd, 2025, amateur astronomer John Sitch was doing what he'd done for decades, scanning the southern skies from his observatory in Chatsworth Island, New South Wales, hunting for stellar explosions. What he found that morning would soon grab the attention of gamma-ray satellites and X-ray telescopes across the solar system. V1935. Centauri announced itself, not with fanfare, but with photons. Sitch's initial detection showed a star where no star had been bright enough to notice before, sitting in the constellation Centaurus at magnitude 5.8, just bright enough for keen-eyed observers in dark locations to spot without binoculars. But this was no ordinary brightening. Within hours of Sitch's discovery report, reaching the Central Bureau for Astronomical Telegrams, space-based observatories began detecting something extraordinary. NASA's Fermi Gamma Ray Space Telescope triggered on high-energy photons streaming from the nova's direction. The Swift Observatory, designed to catch gamma-ray bursts, swiveled its X-ray telescope toward Centaurus and began recording hard X-ray emissions, signatures of violent particle acceleration in the nova's expanding shockwave. These weren't just pretty lights for backyard stargazers. This was evidence of physics operating at extremes. Electrons and protons accelerated to near light speeds. Magnetic fields twisted into knots. Temperatures soaring into the millions of degrees. The nova was essentially a cosmic particle accelerator, hurling matter outward at thousands of kilometers per second. But V1935 Centauri wasn't finished making headlines. Just days later, Sitch struck again, or rather, the cosmos did. V7994 Sagittarius erupted in the neighboring constellation Sagittarius, reaching magnitude 6.2 at discovery. Two stellar explosions, both credited to the same observer, both bright enough for small telescopes or binoculars, both occurring within the same remarkable week. Here's why this pair caught professional astronomers off guard. While novae aren't exceptionally rare, perhaps 10 to 12 occur in our galaxy each year. Having two reach near naked eye brightness within days is genuinely uncommon. The last time observers enjoyed two bright novae simultaneously was during the summer of 2023, and before that, you'd have to reach back several years to find comparable displays. The physics behind these eruptions tells a story of stellar cannibalism played out over cosmic time. Each nova begins with a white dwarf, the dense hot core of a dead star roughly the size of Earth, but with the mass of our Sun. This stellar remnant sits in orbit with a normal star, gradually stealing hydrogen from its companion's outer atmosphere. For years, centuries, or millennia, gas accumulates on the white dwarf's surface, growing denser and hotter under immense gravitational compression. Eventually, temperature and pressure reach a critical threshold. The accumulated hydrogen undergoes runaway thermonuclear fusion, not the controlled burning that powers living stars, but an explosive conflagration that can brighten the binary system by factors of 10,000 or more. The explosion doesn't destroy the white dwarf. Instead, it blows away the surface layer, returning the system to its patient process of accumulation. For observers in Earth's southern hemisphere, both novae occupied prime viewing territory. V 1935. Centauri sits well south of the celestial equator, making it a challenging target for northern observers. VAR 7994 Sagittari, located in the Archer constellation, presents similarly southern viewing geometry, appearing low in the south for mid-northern latitude observers, but riding high in the sky for anyone south of the equator. The discovery process itself reveals the collaborative nature of modern astronomy. Sitch's initial observations, reported through the International Astronomical Union Central Bureau, triggered a cascade of follow-up observations. Within days, observatories around the world were obtaining photometry, precise brightness measurements, and spectroscopy that revealed the characteristic emission lines of hydrogen, helium, and heavier elements in the expanding nova shells. The question that would soon emerge was whether these stellar explosions, occurring during the same week as significant geomagnetic activity and major earthquakes, represented more than coincidence. The mainstream astronomical answer is clear. Novae in neighboring constellations, located thousands of light-years from Earth, pose no direct threat to our planet and exert no measurable influence on terrestrial phenomena. Yet, the timing felt remarkable. At precisely 22 hours, 21 minutes, and 55 seconds, Coordinated Universal Time on September 24th, the Earth's crust beneath Venezuela's Zulia state released energy equivalent to several nuclear weapons. The magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mene Grande, originating from a relatively shallow depth of 7.8 kilometers, close enough to the surface to shake buildings across two nations. The seismic waves propagated outward at roughly 6 kilometers per second through the rock, reaching populated areas within seconds of the rupture. From Maracaibo to Caracas, from Colombian border towns to Caribbean coastal cities, millions of people felt the ground sway beneath their feet. Social media erupted with videos of swinging chandeliers, rattling windows, and residents evacuating buildings as emergency protocols kicked into action across the region. But the Earth wasn't finished. Just 5.5 hours later, at 03:51 and 39 seconds on September the 25th, a second major rupture struck virtually the same location. This time, the magnitude 6.3 earthquake originated from 14 kilometers depth, deeper than its predecessor, but still shallow enough to generate intense surface shaking. The epicenter sat approximately 27 to 28 kilometers east-northeast of Mene Grande, overlapping the first event's rupture zone. To understand why these twin quakes matter, we need to grasp the logarithmic nature of earthquake magnitude scales. A magnitude 6.3 earthquake releases approximately twice the energy of a magnitude 6.2 event. Combined, these two ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release even by global standards. The aftershock sequence provided its own drama. A magnitude 5.8 earthquake struck the same region later on September 25th, following the typical decay pattern that seismologists expect after major ruptures. While 5.8 might sound modest compared to the main shocks, it's still large enough to cause additional damage and maintain anxiety levels among regional populations already stressed by two major events. Regional tectonics explain why this area generates such powerful earthquakes. The Maracaibo Basin sits within a complex zone where the Caribbean plate grinds against the South American plate, creating a network of fault systems, including the Bocono Fault System and the Oca-Ancon-Santa Marta Fault trends. These geological boundaries have been accumulating stress for years, decades, or centuries, storing energy that eventually must be released through sudden slip events. The depth difference between the two main events, 7.8 kilometers versus 14 kilometers, matters significantly for ground shaking intensity. Shallow earthquakes typically produce stronger surface acceleration than deeper events of the same magnitude because seismic waves have less opportunity to spread out and weaken during their journey to the surface. The September 24th event's shallow depth likely contributed to widespread reports of strong shaking across both Venezuela and Colombia. Different seismological agencies reported slightly varying magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey initially reported the first earthquake at magnitude 6.2, while the European Mediterranean Seismological Center and other international monitoring networks provided measurements ranging from 6.1 to 6.3. These differences arise from various factors: different measurement methodologies, updates as additional seismic station data becomes available, and distinctions between moment magnitude, surface wave magnitude, and body wave magnitude calculations. The human impact of these earthquakes extended far beyond seismological statistics. Evacuation orders affected thousands of residents, particularly in multi-story buildings that experienced prolonged swaying during the events. Emergency response teams mobilized across the region, conducting damage assessments and ensuring that critical infrastructure remained operational. While initial reports suggested relatively limited structural damage given the earthquake's magnitudes, assessment teams continued their work for days after the events. The timing raised questions among both professional seismologists and the public. Twin earthquakes within hours, during the same week that twin stars exploded overhead. The human mind naturally seeks patterns, especially when dramatic events cluster in time. In the early morning hours of July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System telescope array detected something extraordinary moving against the background stars. Initial observations suggested a faint comet-like object, but orbital calculations quickly revealed its true nature. 3I Atlas, only the third confirmed interstellar visitor in human history, following the mysterious Oumuamua in 2017 and comet Borisov in 2019. The designation tells the story of its discovery and significance. The 3I prefix indicates the third interstellar object catalogued by the International Astronomical Union, while Atlas credits the telescope system that first spotted this cosmic wanderer. Unlike its predecessors, 3I Atlas arrived during a uniquely favourable observation window, bright enough for detailed study, following a trajectory that keeps it near the ecliptic plane where most solar system activity concentrates, and approaching during solar maximum conditions. The visitor's orbital characteristics reveal its alien origins. Its trajectory shows a hyperbolic shape with an eccentricity significantly greater than 1, indicating it possesses more than enough speed to escape the Sun's gravitational influence. The orbital inclination of approximately 175 degrees means 3I Atlas moves in a retrograde direction relative to the planets, backward compared to the normal flow of solar system traffic. Current models suggest the object measures somewhere between several hundred meters and possibly up to 15 kilometers across, though these size estimates carry substantial uncertainty. Direct imaging remains impossible, even for the largest ground-based telescopes. The visitor appears as nothing more than a fuzzy star-like point of light surrounded by a faint coma of gas and dust. Size estimates depend on assumptions about the object's reflectivity, composition, and activity level, all unknown quantities for an object formed around a different star. What makes 3I Atlas genuinely unique is its timing. This interstellar wanderer entered our solar system during solar cycle 25, when our Sun is at its most active and temperamental. The Sun throws coronal mass ejections into space more frequently during these peak years. Billion-ton clouds of magnetized plasma that race through the inner solar system at speeds exceeding 1 million miles per hour. Space weather forecasters at NOAA's Space Weather Prediction Center were monitoring these solar storms using sophisticated computer models called ENLIL. These simulations track how coronal mass ejections propagate through space, predicting when and where they'll intersect with planets, spacecraft, and other objects in their path. During late September 2025, ENLIL forecasts showed active conditions, multiple coronal mass ejection events threading through the inner solar system during the same days that brought twin novae and twin earthquakes. But here's where this story becomes historically unique. For the first time in recorded human experience, one of these solar storms was on a collision course with an object born in another star system. 3I Atlas was threading through the inner heliosphere during some of solar cycle 25's most active conditions, crossing the same region of space where Earth orbits, prime real estate for encountering solar weather phenomena. We have precedent for what happens when coronal mass ejections collide with comets. In 2007, the European Space Agency's stereo satellites filmed a coronal mass ejection completely severing the ion tail of Comet Encke. The disconnection event, lasting several hours, demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material. If similar interactions occurred with 3I Atlas, we might be witnessing the first documented case of our Sun directly interacting with matter from another stellar neighborhood. The visitor carried material formed around a different star, possibly billions of years ago, material that spent millions of years traveling through the cold void of interstellar space. Now it was approaching the inner solar system, just as our Sun was throwing its worst tantrums. 93 million miles above Venezuela's shaking ground, our star was conducting its own explosive symphony. During the same days that stellar explosions lit up southern skies and earthquakes ruptured South American bedrock, the Sun unleashed coronal mass ejections, billion-ton clouds of magnetized plasma that would cross paths with something unprecedented in human experience: an interstellar visitor. Coronal mass ejections represent some of the most powerful events in our solar system. These eruptions begin in the Sun's corona, where magnetic field lines twist, tangle, and eventually snap like overstressed rubber bands. When magnetic reconnection occurs, it releases energy equivalent to billions of hydrogen bombs, accelerating plasma to speeds between 250 and 3,000 kilometers per second, fast enough to traverse the Earth-Sun distance in 1 to 4 days. NASA's Space Weather Prediction Center tracks these solar storms using the WSA-Enlil model, a sophisticated computer simulation that maps how coronal mass ejections propagate through the heliosphere. The model considers solar wind speed, density, and magnetic field orientation to forecast when and where these plasma clouds will intersect spacecraft, planets, and other objects in their path. During late September 2025, Enlil forecasts showed active conditions, multiple coronal mass ejection events threading through the inner solar system during the same days that brought twin novae and twin earthquakes. Solar cycle 25 reached its peak activity during 2024 and 2025, transforming our typically well-behaved star into a restless giant. The 11-year solar cycle follows a predictable pattern of rising and falling activity, measured by sunspot numbers and solar flare frequency. At solar maximum, the sun's magnetic field becomes chaotic, producing elevated numbers of active regions that can spawn both solar flares and coronal mass ejections. The 10.7 centimeter radio flux, a key indicator of solar activity levels, hovered around 180 to 190 solar flux units during late September. This measurement, taken daily by radio telescopes, correlates strongly with the number and intensity of active regions on the Sun's surface. Values above 150 typically indicate elevated solar activity, while readings above 200 suggest very active conditions, capable of producing major space weather events. But here's where this story becomes historically unique. For the first time in recorded human experience, one of these solar storms was on a collision course with an object born in another star system. 3I Atlas, discovered just 2 months earlier, was threading through the inner heliosphere during some of solar cycle 25's most active conditions. The claim that 3I Atlas was sideswiped by a coronal mass ejection rests on model-based trajectory analysis rather than direct observation. Enlil forecasts suggested that solar storm paths would intersect the interstellar visitor's position during late September. But we must maintain transparency about uncertainty. Space weather models excel at predicting general trends, but struggle with fine details. If the interaction occurred as models suggested, we might expect several observable consequences. Increased ionization could brighten the interstellar visitor's coma, the fuzzy atmosphere of gas and dust surrounding its nucleus. Changes in ion tail morphology might appear in telescopic images as magnetic field disruptions alter how charged particles stream away from the object. Spectroscopic observations could reveal chemical signatures as solar energy liberates specific molecules from the visitor's ancient ice. The physics of coronal mass ejection interactions involves magnetic reconnection, the same process that triggers solar flares and geomagnetic storms. When solar plasma carrying tangled magnetic field lines encounters a comet's ionosphere, field lines can connect, disconnect, and reconnect, releasing energy that accelerates particles and generates observable phenomena. 3I Atlas represents more than just another target for solar weather interactions. As the third confirmed interstellar object, it carries material formed around a different star in a different stellar system, potentially billions of years ago. If solar storms altered its behavior, we were witnessing cosmic history. Around the world, telescopes began swiveling toward the southern sky. From professional observatories perched on remote mountaintops to backyard setups in suburban neighborhoods, a global network of astronomers coordinated their efforts to track the extraordinary convergence unfolding in late September 2025. What started as individual discoveries quickly became a collaborative scientific campaign spanning continents and organizations. The Central Bureau for Astronomical Telegrams, housed at the Harvard-Smithsonian Center for Astrophysics, served as the coordination hub. When John Sitch reported his nova discoveries, the Bureau issued circulars that triggered a cascade of follow-up observations. Circular number 5611 confirmed V1935 Centauri's detection, while 5612 documented V7994 Sagittarius. Within hours, observatories from Australia to Chile were obtaining detailed measurements. Amateur astronomers played crucial roles through organizations like the American Association of Variable Star Observers. Their nightly monitoring provided temporal resolution that professional telescopes, focused on multiple targets, couldn't maintain for individual objects. Visual observers estimated brightness using comparison stars, while those with CCD cameras provided precise magnitude measurements. These observations, contributed by hundreds of amateur astronomers worldwide, revealed subtle variations in the novae's light curves that contained clues about the explosion physics. Meanwhile, space-based observatories were gathering data impossible to obtain from Earth's surface. NASA's Fermi Gamma Ray Space Telescope detected high-energy photons from V1935 Centauri, evidence of particles accelerated to near-light speeds. The Swift Observatory recorded hard X-ray emissions that revealed the nova's most violent aspects. These satellites, orbiting above Earth's atmosphere, could see wavelengths of light that never reached the ground, providing a complete picture of the stellar explosions. For 3I Atlas, observation planning took on additional urgency. Mars orbiters were preparing for the interstellar visitor's closest approach on October 3rd. ESA's ExoMars Trace, Gas Orbiter, and NASA's Mars Reconnaissance Orbiter adjusted their observation schedules to capture this unprecedented encounter. The spacecraft would observe 3I Atlas from positions roughly 28 million kilometers away, offering viewing angles impossible from Earth-based observatories. Ground-based facilities coordinated their own campaigns. The Minor Planet Center collected astrometric measurements that refined 3I Atlas's trajectory. Professional observatories scheduled spectroscopic observations to characterize the visitor's chemical composition. Radio telescopes prepared to detect molecular emissions that could reveal the object's internal structure and activity patterns. Social media became an unexpected coordination tool. Astronomy enthusiasts shared observations in real time through online forums and platforms. When someone spotted changes in 3I Atlas's brightness or tail structure, word spread within hours, prompting others to confirm the observations. This informal network complemented formal scientific channels, creating a truly global observational campaign. NOAA's Space Weather Prediction Center maintained continuous monitoring of solar activity through multiple satellite systems and ground-based observatories. The Advanced Composition Explorer, positioned between Earth and the Sun, provided advanced warning of incoming solar wind disturbances. The Solar Dynamics Observatory delivered continuous high-resolution images of the Sun's surface and corona. Together, these systems tracked the coronal mass ejections threading through the inner solar system during the convergence week. Seismological networks responded to the Venezuelan earthquakes with equal coordination. The United States Geological Survey processed data from monitoring stations across South America. The European Mediterranean Seismological Center contributed measurements from their network. Regional agencies in Venezuela and Colombia mobilized assessment teams to document damage and monitor aftershock sequences. The coordination extended to data sharing and analysis. Raw observations flowed into databases accessible to researchers worldwide. Preliminary results appeared on preprint servers within days of collection. Scientific discussions unfolded in real time through email lists and video conferences, with researchers comparing notes and refining interpretations as new data arrived. This global mobilization represented modern astronomy at its collaborative best. Professional and amateur observers working together, space-based and ground-based instruments complementing each other, real-time communication enabling rapid response to transient phenomena. The convergence of events in September 2025 demanded nothing less than a coordinated worldwide effort. Step back for a moment and consider what we've mapped. Twin stellar explosions visible to the naked eye. Twin magnitude 6 earthquakes rupturing within hours of each other. Coronal mass ejections threading through the inner solar system, and an interstellar visitor crossing our neighborhood during solar maximum conditions. A lot of universe happening very fast, compressed into the final week of September 2025. Let's construct a timeline with precision. On September 23rd, VI 1935, Centauri erupts to naked eye visibility in Centaurus. On September 24th, at 22:21 Coordinated Universal Time, a magnitude 6.2 earthquake strikes Venezuela. On September 25th, VI 7994 Sagittarius explodes in Sagittarius. Just 5.5 hours after the first quake, a magnitude 6.3 earthquake ruptures the same Venezuelan region. A magnitude 5.8 aftershock follows later that same day. Throughout this same window, Enlil models predict coronal mass ejections crossing 3I Atlas's trajectory. The interstellar visitor, discovered just 2 months earlier in July, is navigating the inner solar system during what may be the most active period of solar cycle 25. The geography of these events spans scales that challenge human intuition. The novae erupted in Centaurus and Sagittarius, constellations visible primarily from Earth's southern hemisphere. Their light had travelled thousands of years to reach us, precisely during this remarkable week. The earthquake struck near Mene Grande in northwest Venezuela, in a tectonically complex region where the Caribbean and South American plates grind against each other. The coronal mass ejections propagated through the inner heliosphere, a volume of space larger than Jupiter's orbit. And 3I Atlas was crossing the ecliptic plane, the imaginary disk where most planetary action takes place, threading between Mars and the Sun. This temporal compression of dramatic events across multiple domains creates a narrative structure that feels almost scripted. 2 stars explode within days. 2 major earthquakes rupture within hours. Solar storms thread through space during the same week. An interstellar visitor approaches Mars while carrying material from another stellar system. The clustering transcends simple coincidence and approaches something resembling cosmic synchronicity. But here's the critical question. What does this convergence actually mean? Are we witnessing unrelated phenomena clustering by chance? Or is something more systematic at work? The mainstream scientific answer is clear and consistent. The United States Geological Survey maintains that no demonstrated physical mechanism connects space weather phenomena to earthquake occurrence. Stellar astronomers view novae as predictable consequences of binary star evolution, their timing following stellar physics rather than terrestrial or solar system influences. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution during solar maximum periods. Each phenomenon follows well-understood natural laws operating independently. Stellar physics explains novae. Plate tectonics explains earthquakes. Solar physics explains coronal mass ejections. Orbital mechanics explains comet approaches. The timing, while remarkable, doesn't require exotic explanations or hidden connections. Yet, acknowledging mainstream scientific positions doesn't require dismissing the remarkable nature of this temporal cluster. Sometimes, the universe arranges itself in ways that stretch coincidence toward something approaching poetry, even when underlying mechanisms remain mundane. Human brains evolved to detect meaningful patterns in complex environments, a cognitive capability that served our ancestors well when survival depended on recognizing subtle correlations. This pattern recognition operates automatically, scanning for connections that might indicate causation, even when only correlation exists. The convergence we're documenting represents a data point in cosmic history. Whether it proves meaningful or merely memorable depends on what observations reveal in the coming weeks and months as 3i Atlas continues its journey through the inner solar system. This is where honest science meets human pattern recognition, and the collision isn't always comfortable. Our brains evolved to detect meaningful connections in complex environments. The rustle that might signal a predator, the cloud formation that could bring rain, the behavioral changes that might indicate social threat or opportunity. This cognitive architecture serves us well in many contexts, but it can also lead us to perceive significance in coincidental clustering. The scientific mainstream offers clear guidance on these events. The United States Geological Survey maintains no demonstrated connection between space weather phenomena and earthquake occurrence. Decades of correlation studies have failed to establish reliable predictive relationships between solar activity and seismic events. Professional seismologists emphasize that earthquake prediction remains impossible using current scientific methods, whether based on terrestrial precursors or extraterrestrial influences. Similarly, stellar astronomers view novae as predictable consequences of binary star evolution, occurring when white dwarf stars accumulate sufficient material from companion stars to trigger thermonuclear runaway. The timing of nova eruptions follows stellar physics rather than terrestrial or solar system influences. Volvo, 1935, Centauri and V, 7994 Sagittari represent normal, if visually impressive, examples of processes occurring throughout our galaxy on a regular basis. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution in the Sun's corona. These events occur more frequently during solar maximum periods, making late 2025 a statistically likely time for multiple coronal mass ejection events. The interaction between solar storms and cometary material has been documented extensively, representing well-understood plasma physics rather than exotic phenomena. Yet, acknowledging mainstream scientific positions doesn't require dismissing the remarkable nature of this temporal cluster. Sometimes, the universe arranges itself in ways that stretch coincidence toward something approaching synchronicity, even if the underlying mechanisms remain mundane. The question becomes, how do we hold space for both rigorous skepticism and appropriate wonder? Our approach throughout this exploration will maintain clear boundaries between different types of claims. Observational facts form our foundation. Magnitude measurements, location coordinates, spectroscopic detections represent what instruments recorded, what satellites detected, what seismographs measured. Above this foundation, we'll build layers of scientific interpretation based on established physics and well-tested models. Beyond established science lies the realm of speculation, where we'll venture carefully and with clear labeling. Speculative connections, possible relationships between solar activity and terrestrial phenomena, potential influences of stellar events on solar system dynamics, hypothetical mechanisms linking cosmic and geological processes, deserve exploration provided we maintain transparency about their status as hypotheses rather than facts. The vocabulary of cosmic events requires definition for general audiences. A nova represents a stellar explosion that brightens a binary star system by factors of thousands or millions, caused by thermonuclear runaway on a white dwarf surface. It differs fundamentally from a supernova, which destroys the exploding star entirely. A coronal mass ejection consists of billion-ton plasma clouds launched from the Sun at speeds of hundreds to thousands of kilometers per second. What's coming in our investigation will separate observed phenomena from imagined connections, while maintaining respect for both scientific rigor and human curiosity. We'll examine the detailed physics of stellar explosions, earthquake ruptures, and solar storm interactions. We'll track 3I Atlas through its Mars flyby on October 3rd and perihelion approach on October 29th. We'll explore legitimate scientific hypotheses alongside clearly labelled speculation about more exotic possibilities. The most scientifically honest position acknowledges both the theoretical possibilities and the empirical limitations. Our commitment involves presenting multiple perspectives honestly. Mainstream scientific explanations deserve primary attention because they rest on established physics. Speculative hypotheses deserve consideration, provided they remain clearly distinguished from proven science. The human impulse to find meaning in apparent patterns deserves respect, even when scientific evidence doesn't support causal connections. Picture a white dwarf star, a sphere roughly the size of Earth, but containing the mass of our entire Sun. Its surface gravity crushes matter to densities approaching 1 million times that of water. Surface temperatures hover around 50,000 degrees Fahrenheit. This stellar corpse represents what remains after a sun-like star exhausts its nuclear fuel, sheds its outer layers, and collapses into a sphere of degenerate matter where atoms exist in states impossible under terrestrial conditions. Now, imagine this cosmic furnace locked in orbital dance with a normal star, perhaps a red giant whose outer atmosphere has swollen to massive proportions as it ages. Gravity from the white dwarf gradually strips hydrogen from its companion's extended atmosphere, pulling gas across the space between stars in streams that spiral inward like water circling a drain. This stolen material accumulates on the white dwarf's surface, growing denser and hotter under crushing gravitational compression. For decades, centuries, or millennia, hydrogen accumulates. Temperature and pressure climb steadily as more material piles onto the white dwarf surface. Unlike the controlled nuclear fusion occurring in stellar cores, this process builds toward explosive release. When temperature reaches roughly 100 million degrees Kelvin, thermonuclear runaway begins. The explosion that creates a nova like V1935 Centauri occurs in seconds. Runaway fusion consumes the accumulated hydrogen layer in a conflagration that releases energy equivalent to our Sun's total output over thousands of years. But here's the crucial difference from a supernova. The white dwarf itself survives. The explosion blows away only the surface layer of stolen material, leaving the underlying stellar remnant intact and ready to begin the process again. This is why V1935, Centauri's high-energy signatures, captured attention worldwide. When NASA's Fermi Gamma Ray Space Telescope detected gamma rays from the nova's direction, it was recording evidence of particles accelerated to near light speeds in the explosion's shock fronts. The Swift Observatory's hard X-ray detections revealed electrons spiraling through magnetic fields at enormous energies, creating synchrotron radiation across the electromagnetic spectrum. These high-energy phenomena transform novae from simple brightening events into cosmic particle accelerators. The expanding shell of ejected material, racing outward at speeds of several thousand kilometers per second, creates shockwaves when it collides with the sparse gas between stars. These shocks function like natural cyclotrons, using magnetic field acceleration to boost protons and electrons to energies that would require massive terrestrial laboratories to achieve. The brightness evolution follows patterns established by decades of nova study. The initial rise from invisibility to naked eye magnitude typically occurs over days to weeks. Peak brightness may last anywhere from days to months, depending on the white dwarf's mass, the accretion rate from its companion, and the composition of the ejected material. The decline phase can extend over months or years, sometimes interrupted by secondary peaks, as different physical processes dominate the nova's energy output. Spectroscopy reveals the nova's chemical fingerprints. Early spectra typically show broad emission lines of hydrogen, helium, and heavier elements moving at high velocities, evidence of the expanding ejecta. As the nova evolves, these lines narrow and shift as the ejected material cools and decelerates. Eventually, forbidden lines appear, transitions that can only occur in the extremely low-density environments of expanding nova shells, where atoms may go hours or days between collisions. The distances to V1935, Centauri and V7994 Sagittari remain uncertain, but probably exceed several thousand light-years. This means the explosions we observed in September 2025 actually occurred millennia ago, when human civilization was just beginning to develop agriculture. The light from these stellar explosions traveled through interstellar space longer than recorded human history, arriving at Earth precisely during this remarkable week. When NASA's Fermi Gamma Ray Space Telescope triggered on high-energy photons streaming from V1935 Centauri's direction, it wasn't just recording pretty lights. This was evidence of physics operating at the most extreme scales accessible to observation. Gamma rays represent the highest energy form of electromagnetic radiation, photons carrying millions of times more energy than visible light. Their detection from a nova reveals that something extraordinary is happening in the explosion's aftermath. The process begins with the nova's expanding shockwave. When the thermonuclear explosion blows material off the white dwarf's surface at thousands of kilometers per second, this fast-moving ejecta slams into the sparse gas surrounding the binary star system. The collision creates shock fronts, regions where matter suddenly compresses and heats to extreme temperatures. These shocks don't just heat gas, they accelerate charged particles. Think of these shock fronts as cosmic particle accelerators, natural versions of the massive machines physicists build on Earth. Magnetic fields tangled within the expanding nova shell act like invisible rails, bouncing electrons and protons back and forth across the shock boundary. With each crossing, particles gain energy. After many crossings, some particles reach speeds approaching the speed of light, becoming what physicists call relativistic particles. When relativistic electrons spiral through magnetic fields, they emit synchrotron radiation. This process produces photons across the entire electromagnetic spectrum, from radio waves through visible light all the way up to X-rays and gamma rays. The Swift Observatory detected these hard X-rays from V1935 Centauri, confirming that the nova was indeed accelerating particles to enormous energies. The gamma ray detections reveal something even more remarkable. These highest energy photons suggest particle acceleration, operating more efficiently than previously thought possible in nova environments. Traditional models predicted that novae would produce some high-energy radiation, but observations from Fermi and other satellites show that novae can be prolific gamma-ray sources, sometimes outshining the entire rest of the nova in gamma-ray brightness. Several mechanisms might explain this efficient particle acceleration. Magnetic reconnection, the same process that triggers solar flares and coronal mass ejections, could be operating within the nova's magnetic field. When tangled magnetic field lines suddenly snap and reconnect in new configurations, they can release enormous amounts of stored magnetic energy directly into particle acceleration. This process converts magnetic field energy into kinetic energy of charged particles almost instantaneously. Another possibility involves shock acceleration operating in multiple stages. The initial nova explosion creates one set of shocks. As this material expands outward, it may encounter additional structures, perhaps shells of material from previous nova eruptions or dense regions of the binary system's stellar wind. Each new collision creates fresh shocks, providing multiple opportunities for particles to gain energy through repeated acceleration. The gamma-ray emissions also reveal information about the nova's environment. High-energy photons interact with matter and magnetic fields in distinctive ways. By analyzing the gamma-ray spectrum, the energy distribution of detected photons, astronomers can infer properties of the magnetic field strength, the density of surrounding gas, and the efficiency of particle acceleration processes. For V1935, Centauri, the Fermi detections place it among an emerging class of gamma-ray novae that challenge traditional understanding. Not all novae produce detectable gamma rays. Those that do seem to share certain characteristics, possibly related to the strength of magnetic fields in the binary system, or the speed of the ejected material. Understanding what makes some novae efficient gamma-ray producers, while others remain quiet at high energies, represents an active area of research. The detection of gamma rays from novae bridges the gap between different classes of cosmic explosions. Supernovae, vastly more energetic than novae, are known gamma-ray producers. Active galactic nuclei, powered by supermassive black holes, emit copious gamma rays. Finding that novae also accelerate particles to relativistic energies suggests that similar physical processes operate across wildly different scales. Beneath Lake Maracaibo and the surrounding Zulia state of Venezuela lies one of South America's most tectonically complex regions. The Caribbean plate grinds against the South American plate along a boundary zone that includes multiple fault systems. The Bocono fault system running northeast-southwest through the Venezuelan Andes, the Oca-Ancon fault trending east-west along the Caribbean coast, and the Santa Marta fault extending into Colombia. These geological boundaries have been accumulating stress for decades, storing energy that must eventually be released through sudden slip events. The magnitude 6.2 earthquake at 22:21 Coordinated Universal Time on September 24th began as a rupture along one of these fault segments, approximately 7.8 kilometers beneath the surface. At this relatively shallow depth, seismic waves had less opportunity to spread out and weaken during their journey to the surface, amplifying ground acceleration across a broad region. The initial rupture probably extended several kilometers along the fault plane, with sudden displacement measured in meters, releasing stress that had been building for years or decades. Seismic waves propagated outward from the rupture zone at roughly 6 kilometers per second through the surrounding rock. Primary waves, compressional disturbances that cause back and forth motion along their direction of travel, arrived first at seismograph stations across the region. Secondary waves followed, creating the side-to-side motion that typically causes the most damage to structures. Surface waves, traveling more slowly but often carrying the most destructive energy, produced the rolling motions that eyewitnesses described as lasting for minutes in some locations. Just 5.5 hours later, at 03:51 on September 25th, a second major rupture struck virtually the same region. The magnitude 6.3 earthquake originated from 14 kilometers depth, deeper than its predecessor, but still shallow enough to generate intense surface shaking. This second event likely occurred on an adjacent fault segment, triggered by stress changes created by the first rupture. The physics of stress transfer explains why earthquakes often occur in clusters. When one fault segment suddenly slips, it changes the stress field on nearby fault segments. Some areas experience increased stress, making them more likely to rupture in the near future. Other areas experience stress relief, becoming temporarily less likely to generate earthquakes. The September 24th rupture apparently loaded stress onto the fault segment that failed 5.5 hours later. The magnitude difference between 6.2 and 6.3 earthquakes might seem trivial, but the logarithmic nature of the magnitude scale means the second event released approximately twice as much energy as the first. Combined, these twin ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release that ranks among the largest global seismic events of late September 2025. International seismological agencies reported slightly different magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey uses moment magnitude, calculated from the total energy released during the rupture. The European Mediterranean Seismological Center may use different magnitude scales based on surface wave amplitudes or body wave characteristics. These methodological differences, combined with updates as additional seismograph data becomes available, explain why headlines reported magnitude ranges from 6.1 to 6.3 for the first event. The aftershock sequence followed patterns that seismologists have documented for decades. The magnitude 5.8 earthquake that struck later on September 25th represents a typical large aftershock, smaller than the main shock, but still significant enough to cause additional damage and concern. Omori's law, formulated in the early 1900s, describes how aftershock frequency decays over time following major earthquakes. The largest aftershocks typically occur within days of the main shock, with smaller events continuing for weeks, months, or even years. Human impact from these earthquakes extended across both Venezuela and Colombia. The relatively shallow depths amplified surface shaking, leading to evacuation orders for high-rise buildings in major cities. Social media filled with videos of swinging light fixtures, rattling windows, and people evacuating buildings as emergency protocols activated across the region. While initial damage reports remained limited given the earthquake's magnitudes, assessment teams spent days documenting both visible structural damage and potential long-term weakening of buildings and infrastructure. The regional geology helps explain why this area generates such powerful earthquakes. The Maracaibo Basin formed through complex interactions between the Caribbean and South American plates, creating a network of fault systems that accommodate ongoing tectonic motion. Lake Maracaibo itself sits within a graben, a down-dropped block bounded by normal faults that continue to experience active deformation. The petroleum deposits that make this region economically important formed in sedimentary basins created by the same tectonic processes that generate earthquakes. Depth measurements carry significant uncertainty, especially for earthquakes occurring in geologically complex regions. The 7.8 kilometer depth reported for the first event and 14 kilometer depth for the second represent best estimates based on seismic wave arrival times at multiple monitoring stations. These depths place both earthquakes in the upper crust, where brittle fracture dominates over the ductile deformation that occurs at greater depths where temperature and pressure increase. The timing of these events raised questions about potential triggers. Could solar activity, atmospheric pressure changes, or other external factors influence earthquake occurrence? The scientific consensus, supported by the United States Geological Survey and international seismological organizations, maintains that no reliable correlation exists between space weather and earthquake activity. Decades of statistical analysis have failed to establish predictive relationships between solar flares, coronal mass ejections, geomagnetic storms, and seismic events. However, some research has explored more subtle potential connections. Changes in atmospheric pressure can alter stress on fault systems by tiny amounts, typically far smaller than the stress changes caused by earth tides from lunar and solar gravitational effects. While these influences remain detectable with sensitive instruments, they fall orders of magnitude below the stress changes needed to trigger earthquakes on faults that aren't already very close to failure. The Global Centroid Moment Tensor Database provides detailed analyses of fault orientations, slip directions, and rupture mechanisms for both Venezuelan earthquakes. These analyses reveal which fault planes actually moved and in what directions, information that helps seismologists understand regional stress fields and predict which fault segments might experience elevated risk in the future. Could larger earthquakes follow in the same region? The geological setting certainly allows for more powerful events. The fault systems around Lake Maracaibo have generated magnitude 7 earthquakes historically, and the regional tectonics suggest that such events will continue occurring irregularly over geological time. However, seismologists cannot predict whether days, years, or decades might pass before the next major rupture. Solar cycle 25 reached its peak activity during 2024 and 2025, transforming our typically well-behaved star into a restless giant capable of hurling billion-ton plasma clouds across the solar system. On the same days that stellar explosions lit up southern skies and earthquakes shook Venezuelan bedrock, solar activity indices painted a picture of a sun operating near maximum fury. The 10.7 centimeter radio flux, a key indicator of solar activity levels, hovered around 180 to 190 solar flux units during late September. This measurement, taken daily by radio telescopes, correlates strongly with the number and intensity of active regions on the Sun's surface. Values above 150 typically indicate elevated solar activity, while readings above 200 suggest very active conditions capable of producing major space weather events. Sunspots themselves tell the story of magnetic chaos unfolding in the Sun's photosphere. These dark regions, often larger than Earth, form where powerful magnetic field lines punch through the solar surface and suppress normal convective heat transport. The magnetic field strength in sunspot cores can exceed 3,000 Gauss, roughly 6,000 times stronger than Earth's magnetic field at the surface. More sunspots generally mean more opportunities for magnetic field lines to tangle, reconnect, and explosively release energy as solar flares and coronal mass ejections. But raw sunspot numbers only hint at the complexity of solar maximum conditions. The Sun's magnetic field during peak activity resembles a twisted, knotted mess, rather than the relatively simple dipole field that dominates during solar minimum. Active regions, collections of sunspots connected by loops of magnetic field, can persist for weeks or months, rotating across the solar disk and occasionally producing spectacular eruptions visible to spacecraft throughout the inner solar system. The Sun's 11-year cycle follows a predictable pattern of rising and falling activity. At solar minimum, the Sun's surface appears relatively quiet, with few or no visible sunspots for days or weeks at a time. As the cycle progresses toward maximum, sunspot numbers increase dramatically. The Sun's magnetic poles actually flip during this transition, with the north magnetic pole becoming the south, and vice versa. This magnetic reversal reflects the fundamental reorganization of the Sun's internal magnetic field structure. Solar maximum doesn't arrive as a single peak, but often shows a double-peaked pattern with initial high activity, followed by a slight decline, and then a second peak. The current solar maximum appears to be following this pattern, with elevated activity persisting through 2025 and potentially into 2026. This extended maximum phase means elevated space weather risks may continue longer than typical cycles. The Solar Dynamics Observatory provides continuous high-resolution images of the Sun's surface and corona in multiple wavelengths of extreme ultraviolet light. These images reveal the intricate structure of active regions, the towering loops of plasma suspended by magnetic fields, and the sudden brightening that signals solar flare eruptions. The observatory captures images every few seconds, creating time-lapse movies that show how solar magnetic fields evolve and occasionally explode. Coronal mass ejections represent the most dramatic manifestation of solar maximum physics. These events begin when magnetic field lines in the Sun's corona become so twisted and stressed that they suddenly snap and reconnect, converting magnetic energy into kinetic energy of charged particles. The process launches billion-ton clouds of plasma into space at speeds ranging from 250 kilometers per second for slow events to over 3,000 kilometers per second for the fastest eruptions. During late September 2025, this magnetic chaos was operating at peak intensity, creating the active space weather environment that would interact with 3I Atlas during its approach through the inner solar system. We have precedent for what happens when coronal mass ejections collide with comets. The interaction isn't subtle speculation. It's documented physics, captured by spacecraft cameras and analysed in peer-reviewed literature. In 2007, the European Space Agency's stereo satellites filmed a coronal mass ejection, completely severing the ion tail of Comet Encke. The disconnection event, lasting several hours, demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material. Comet tails form through two distinct processes, each responding differently to solar influence. Dust tails curve gracefully away from the Sun, pushed by radiation pressure, the gentle but persistent force of sunlight striking microscopic particles. These dust grains, typically less than 1 micrometer across, act like tiny solar sails. As photons bounce off their surfaces, they transfer momentum that gradually pushes the particles away from the Sun along curved trajectories. Ion tails, by contrast, stretch straight away from our star, following magnetic field lines embedded in the solar wind. These tails form when ultraviolet light from the Sun strips electrons from gas molecules in the comet's coma, creating charged particles called ions. Once ionized, these particles become electromagnetically coupled to the solar wind's magnetic field, forced to flow along magnetic field lines like beads on invisible strings. When a coronal mass ejection disrupts these magnetic connections, ion tails can disconnect entirely, drift away from the comet, and eventually dissipate while new tails form from fresh material. The stereo footage of Comet Encke showed this process in remarkable detail. As the coronal mass ejection's magnetic field swept past the comet, the existing ion tail suddenly separated from the nucleus, forming a distinct cloud of ionized gas that drifted away into space. Within hours, a new ion tail began forming as fresh gas from the comet's coma became ionized and coupled to the post-coronal mass ejection magnetic field. The physics involves magnetic reconnection, the same process that triggers solar flares and powers the aurora. When magnetic field lines with different orientations encounter each other, they can break and reconnect in new configurations. This reconnection releases enormous amounts of stored magnetic energy, accelerating charged particles and creating the electrical currents that flow through space plasma. For comets, this means the magnetic field lines connecting their ion tails to the solar wind can suddenly snap when a coronal mass ejection passes. The disconnection occurs at the boundary, where the comet's weak magnetic environment meets the strong, turbulent magnetic fields carried by the coronal mass ejection. The result is a spectacular severing of the ion tail, visible in telescopic images as a distinct break between the comet's head and its tail. If 3I Atlas experienced similar interactions during late September 2025, we might expect observable consequences. Increased ionization could brighten the interstellar visitor's coma, as solar energy liberates more gas molecules from the nucleus and ionizes them more efficiently. Changes in ion tail morphology might appear in telescopic images as magnetic field disruptions alter how charged particles stream away from the object. 3I Atlas represents far more than a curiosity from interstellar space. It's potentially the most sensitive natural probe we've ever had for studying how our sun interacts with material formed around other stars. While Oumuamua departed too quickly for detailed study, and Borisov remained relatively distant throughout its passage, this third interstellar visitor offers unprecedented opportunities to observe solar weather effects on matter that spent millions of years wandering between stellar systems. The geometry alone makes 3I Atlas extraordinary for heliospheric science. Unlike previous interstellar objects that followed highly inclined trajectories through the outer solar system, this visitor threads through the ecliptic plane where solar wind density, magnetic field strength, and space weather activity reach their highest intensities. It's approaching during solar cycle 25 maximum conditions, when coronal mass ejection frequency peaks and solar magnetic field complexity reaches maximum chaos. Think of comets as natural magnetometers and plasma diagnostics floating through space. Their ion tails provide visible evidence of invisible magnetic field lines embedded in the solar wind. Changes in tail orientation, brightness, and morphology reveal information about solar wind speed, density, magnetic field direction, and the passage of shock waves or other disturbances. Professional space weather researchers have used solar system comets as remote sensors for decades, extracting quantitative measurements of space plasma conditions from telescopic observations. 3I Atlas potentially extends this capability to material with entirely different formation history and chemical composition. While solar system comets condensed from the same primordial disk that formed our planets, this interstellar visitor carries volatiles created around a different star in a different stellar system, possibly billions of years ago. The ice locked within its nucleus formed under conditions that may have been drastically different from those in our early solar system. Consider what this means for understanding interstellar chemistry. The gas molecules sublimating from 3I Atlas's surface as solar heating increases carry direct information about chemical processes operating in another stellar neighborhood. Spectroscopic observations could reveal whether the visitor contains the same mix of water ice, carbon monoxide, carbon dioxide, and organic compounds found in solar system comets, or whether its composition reflects different stellar nucleosynthesis patterns and chemical evolution pathways. The visitor's trajectory brings it through multiple space weather environments, from the relatively quiet conditions of interstellar space to the intense activity near solar maximum. This natural experiment allows astronomers to observe how cosmic radiation and magnetic fields affect interstellar material over time. Has millions of years of cosmic ray exposure altered the visitor's chemical composition? Have interstellar magnetic fields modified its structure? These questions couldn't be answered for previous interstellar visitors, but might become accessible through careful observation of 3I Atlas. Current models suggest the object measures somewhere between several hundred meters and possibly up to 15 kilometers across, though these size estimates carry substantial uncertainty. The actual size matters enormously for understanding how solar heating penetrates into the nucleus and what fraction of the object's volatile inventory might be liberated during its perihelion passage. Amateur astronomers worldwide were positioned to document changes in the visitor's appearance. The global network of comet observers, connected through online forums and observing organizations, maintains nightly monitoring of interesting objects. Their images, when compared across time, reveal subtle changes in brightness, tail structure, and coma morphology that often escape detection by professional observatories focused on other targets. 3i Atlas carries material from another stellar system, crossing through our Sun's domain during its most active phase. Whatever happens next would reveal how stars interact with interstellar matter. The autumn equinox season traditionally amplifies space weather effects through a phenomenon known as the Russell-McPherron effect. This geometric coupling arises from the orientation of Earth's magnetic field relative to the interplanetary magnetic field carried by the solar wind. During equinox periods, the geometry favors magnetic reconnection between solar, wind magnetic fields and Earth's magnetosphere, often producing intense geomagnetic storms, even from relatively modest solar disturbances. Understanding this effect requires visualizing Earth's magnetic field as a giant bar magnet tilted relative to our planet's rotation axis. The magnetic poles don't align perfectly with the geographic poles, sitting about 11 degrees off-axis. This tilt creates a geometry that changes throughout the year as Earth orbits the Sun. During the March and September equinoxes, when day and night have equal length, the angle between Earth's magnetic field and the incoming solar wind reaches its most favorable configuration for magnetic reconnection. Magnetic reconnection is the key process that allows solar wind energy to enter Earth's magnetosphere. When magnetic field lines from the Sun and Earth have opposite orientations, they can break apart and reconnect in new configurations, creating pathways for solar plasma to flow into the magnetosphere. This process releases enormous amounts of stored magnetic energy, accelerating charged particles and generating the electrical currents that power the aurora. The Russell-McPherron effect explains why geomagnetic storms occur more frequently and reach greater intensity during spring and fall compared to summer and winter. Statistical analyses of decades of space weather data show clear peaks in geomagnetic activity around the equinoxes. September and October historically produce some of the year's most spectacular auroral displays and most significant space weather impacts on technology. For late September 2025, this seasonal enhancement provided additional context for elevated space weather activity. The combination of solar cycle 25 maximum conditions and favorable Russell-McPherron geometry created optimal prospects for significant geomagnetic disturbances. Space weather forecasters expected enhanced aurora visibility at lower latitudes than typical quiet conditions would allow. The practical implications extend beyond beautiful light shows. Geomagnetic storms can disrupt high-frequency radio communications used by aviation and maritime industries. Satellite operators must adjust spacecraft orbits due to increased atmospheric drag when the upper atmosphere heats and expands during storms. Power grid operators monitor space weather forecasts because intense geomagnetic activity can induce electrical currents in long transmission lines, potentially causing transformer damage or widespread blackouts. Novae maintains scales for different types of space weather impacts. The G scale rates geomagnetic storms from G1 minor to G5 extreme. The S scale rates solar radiation storms based on energetic particle flux. The R-scale rates radio blackouts caused by solar flares ionizing Earth's upper atmosphere. These scales help various industries prepare for and respond to space weather effects. The Russell-McFerran effect doesn't create space weather, it amplifies the impact of whatever space weather occurs. A coronal mass ejection arriving during equinox season produces stronger geomagnetic disturbances than the same coronal mass ejection arriving during solstice periods. This geometric amplification meant that the coronal mass ejections threading through the inner solar system during late September could produce more dramatic terrestrial effects than they might during other seasons. For 3I Atlas, the seasonal timing was coincidental rather than causal. The interstellar visitor's trajectory brought it through the inner solar system according to orbital mechanics determined millions of years ago when gravitational interactions with another stellar system sent it on its long journey. That this passage happened to occur during both solar maximum and autumn equinox represented fortunate timing for observations, but reflected no deeper connection between these independently determined cycles. The idea that solar storms might influence earthquake occurrence represents one of the most persistent and controversial hypotheses in Earth-space science. For decades, researchers have reported statistical correlations between various space weather phenomena and seismic activity. Yet no widely accepted physical mechanism explains how electromagnetic disturbances 93 million miles away could trigger sudden ruptures in Earth's crust. The most intriguing recent hypothesis comes from researcher Stefan Burns, who proposed that drops in solar wind density following high-speed streams could create a kind of electromagnetic vacuum that might subtly alter crustal stress fields. According to this model, when dense, fast-moving solar wind suddenly gives way to sparse, slow background solar wind, the change in electromagnetic pressure on Earth's magnetosphere could theoretically propagate through complex coupling mechanisms to influence stress accumulation on fault systems. The physics would involve multiple steps, each introducing uncertainty and attenuation. First, solar wind density variations would alter the shape and pressure of Earth's magnetosphere, the magnetic bubble that shields us from most space weather effects. Changes in magnetospheric configuration could modify electric currents flowing through the ionosphere, Earth's electrically conductive upper atmosphere. These current variations might induce electromagnetic fields that propagate into Earth's crust, where they could theoretically influence piezoelectric stress in crystalline rock structures. Each step in this proposed causal chain involves effects measured in nanotesla magnetic field variations or microstrain stress changes, quantities thousands of times smaller than the stress changes needed to trigger earthquakes on fault systems that aren't already extremely close to failure. The theoretical coupling mechanisms exist, but their magnitudes appear insufficient to influence seismic activity under normal circumstances. What's actually established scientifically is extensive literature of correlation claims, coupled with conspicuous absence of causal demonstration. Studies dating back decades have reported statistical associations between solar flare activity and earthquake occurrence, geomagnetic storm intensity, and seismic event clustering, and various space weather indices and regional earthquake catalogues. These correlations often appear statistically significant when first reported, but frequently fail to replicate when tested against different time periods, geographic regions, or earthquake catalogues. Publication bias complicates the picture significantly. Positive correlations between space weather and earthquakes are more likely to be submitted, accepted, and cited than null results that find no relationship. This creates an artificial impression of scientific consensus around connections that may not exist or may be far weaker than published literature suggests. Meta-analyses attempting to synthesize multiple studies often find that effect sizes decrease as sample sizes increase and methodological rigor improves. The United States Geological Survey's official position, supported by international seismological organizations, maintains that no reliable correlation has been demonstrated between space weather and earthquake occurrence. This conclusion rests on extensive statistical analysis of global earthquake catalogues compared against comprehensive space weather databases spanning multiple solar cycles. When proper statistical controls are applied, correcting for multiple comparisons, temporal clustering, and selection bias, most reported correlations disappear or become statistically insignificant. The challenge of testing space weather-earthquake connections lies in separating genuine physical relationships from statistical artifacts. Earthquake occurrence follows complex patterns, including aftershock sequences, spatial clustering, and temporal correlations that can easily generate spurious correlations with any time-varying external phenomenon. The scientific method demands a critical distinction between correlation and causation. Two phenomena occurring simultaneously or in sequence doesn't necessarily mean one caused the other. This fundamental principle becomes especially important when examining claims about space weather influencing earthquakes, where the temptation to see patterns can overwhelm careful statistical reasoning. Consider a simple example. Ice cream sales and drowning deaths both increase during summer months. The correlation is real and measurable, but buying ice cream doesn't cause drowning. Instead, both phenomena share a common cause: warm weather that brings people to beaches and pools while simultaneously increasing demand for cold treats. This illustrates how correlations can emerge from shared external factors rather than direct causal relationships. Earthquake occurrence presents even more complex statistical challenges. Seismic events don't happen randomly, but follow patterns shaped by tectonic stress accumulation, aftershock sequences, and spatial clustering along fault networks. Any time-varying phenomenon, whether space weather, lunar phases, or atmospheric pressure changes, will occasionally appear to correlate with earthquake clusters simply by chance. The problem multiplies when researchers examine historical data looking for correlations. This approach, called data mining or p-hacking in its most problematic form, involves testing numerous potential relationships until something appears statistically significant. With enough variables and time windows, random chance alone guarantees some correlations will emerge. The critical question becomes, do these correlations persist when tested against new independent datasets? Most reported space weather earthquake correlations fail this replication test. A study might find that magnitude 6 or larger earthquakes occur more frequently during geomagnetic storms in Japan between 1990 and 2010. But when other researchers examine different regions, different time periods, or different magnitude thresholds, the correlation disappears. This pattern of non-replication strongly suggests the original finding reflected statistical noise rather than genuine physical relationships. Proper hypothesis testing requires pre-registration, where researchers specify their predicted relationships, statistical methods, and success criteria before examining the data. This prevents the unconscious bias of adjusting analysis methods until desired results emerge. Blind testing protocols, where researchers analyze earthquake catalogs without knowing corresponding space weather conditions, provide additional protection against confirmation bias. Such rigorous approaches remain rare in space weather. Earthquake literature. The September 2025 convergence provides another example of why individual coincidences prove nothing about systematic relationships. Twin earthquakes occurring during a week of elevated space weather activity creates a compelling narrative. But Venezuela sits in a tectonically active region, where magnitude 6 earthquakes occur irregularly, based on plate boundary dynamics. Solar cycle 25 was expected to produce elevated space weather activity during late 2025, regardless of seismic events. The temporal overlap, while striking, doesn't demonstrate causation. Statistical significance itself can be misleading. A finding might achieve the conventional threshold of p less than 0.05, meaning less than 5% probability the result occurred by chance. But this threshold was chosen arbitrarily and doesn't account for multiple testing problems. If researchers test 20 different potential space weather earthquake correlations, one will typically appear significant purely by chance, even if no real relationships exist. Effect size matters more than statistical significance for practical purposes. Even if some subtle space weather influence on earthquakes exists, the question becomes, is it large enough to matter? If space weather changes earthquake timing by minutes or hours on faults already at the brink of failure, this represents a negligible effect compared to decades of tectonic stress accumulation. Such minuscule influences, even if real, provide no useful predictive information. The burden of proof rests on those claiming connections between space weather and earthquakes. Extraordinary claims require extraordinary evidence. The null hypothesis that these phenomena operate independently represents the default scientific position until compelling evidence demonstrates otherwise. Decades of correlation studies have failed to meet this burden. Earth tides caused by lunar and solar gravitational variations demonstrably influence earthquake occurrence. This represents one of the few external factors that shows genuine, measurable effects on seismic activity. Unlike the controversial electromagnetic mechanisms proposed for space weather earthquake connections, gravitational tidal forces operate through well-understood physics that directly alters stress on fault systems. The Moon's gravity creates bulges in Earth's oceans, atmosphere, and even the solid crust itself. As our planet rotates beneath the Moon's gravitational pull, these tidal bulges sweep around the globe twice daily. The Sun contributes similar but weaker tidal effects. When lunar and solar tides align during new and full moons, their combined gravitational pull creates spring tides with maximum tidal stress. When they work at right angles during quarter moons, naiap tides produce minimum tidal stress. These gravitational tides alter stress on fault systems by measurable amounts. The maximum tidal stress change reaches roughly 10 kilopascals, equivalent to the pressure change experienced when diving 1 meter underwater. While this sounds modest, statistical studies of large earthquake catalogs show subtle but genuine correlations between tidal stress and earthquake timing. The effect appears strongest for thrust-faulting earthquakes occurring along subduction zones, where one tectonic plate dives beneath another. The key difference between gravitational and electromagnetic influences involves the directness of the coupling. Tidal forces act directly on Earth's crust through gravity, one of nature's fundamental forces. No complex chain of intermediate processes attenuates the effect. The stress change imposed by tides adds directly to existing tectonic stress, potentially advancing rupture timing on faults already near failure. Research published in prestigious journals demonstrates these tidal correlations withstand rigorous statistical testing. Studies examining tens of thousands of earthquakes worldwide find that large earthquakes occur slightly more frequently during periods of maximum tidal stress. The effect size remains small. Tides don't cause earthquakes, but rather influence their precise timing by hours or days on faults already loaded to near failure conditions. Could similar gravitational effects from other astronomical sources influence seismic activity? Planetary alignments, while popular in some alternative theories, produce gravitational effects orders of magnitude smaller than lunar tides. Even large planetary conjunctions generate tidal forces on Earth, negligible compared to normal lunar-solar tidal variations. Jupiter, the solar system's most massive planet, exerts maximum tidal force on Earth, roughly 1/10,000th that of the Moon, despite being 300 times more massive, simply because distance matters enormously for gravitational effects. The inverse square law governs gravitational force. Doubling the distance reduces gravitational pull by a factor of 4. Jupiter orbits roughly 5 times farther from the Sun than Earth, meaning typical Earth-Jupiter distances exceed 1,000 times the Earth-Moon distance. This vast separation reduces Jupiter's gravitational influence to negligible levels despite its enormous mass. Some researchers have proposed that planetary positions might somehow modulate solar activity, which could then influence Earth through space weather mechanisms. This hypothesis requires 2 speculative leaps: that planetary gravitational effects significantly alter solar magnetic field evolution, and that space weather then influences earthquakes. Neither link has been demonstrated convincingly, despite decades of investigation. The idea that stellar explosions might influence Earth's climate operates across vastly different scales of energy, distance, and time than the space weather earthquake hypothesis. While nearby supernovae could theoretically affect our planet's atmosphere and climate over geological timescales, ordinary novae like V 1935, Centauri, and V 7994 Sagittari are energetically far weaker and astronomically more distant, making any short-term terrestrial impact virtually impossible. Let's establish the scales involved with ruthless precision. A typical nova releases energy equivalent to our Sun's total output over roughly 10,000 years, approximately 10 to the 43rd power joules. This sounds enormous by human standards, capable of powering our entire civilization for billions of years at current consumption rates. However, this energy spreads spherically outward from the explosion site, diluting according to the inverse square law as it travels through interstellar space. V 1935. Centauri likely sits several thousand light-years from Earth, meaning its explosion occurred millennia before human civilization developed writing, agriculture, or permanent settlements. By the time this ancient stellar violence reaches our solar system, the energy flux has diminished to levels comparable to bright starlight. beautiful to observe, utterly negligible in terms of climate forcing or atmospheric chemistry. The energy that finally arrives at Earth from these September novae amounts to perhaps a few extra photons per square meter, less additional radiation than you'd receive from a flashlight held at arm's length. To put this in climate context, the total energy Earth receives from both novae, combined over their entire brightening and decline phases, would be insufficient to warm a single coffee cup by measurable amounts. Contrast this with nearby supernovae, which represent genuine candidates for astronomical climate influence over geological timescales. A supernova occurring within roughly 50 light-years of Earth could potentially deliver enough high-energy radiation to alter atmospheric chemistry significantly. The gamma rays and X-rays from such an explosion might destroy substantial portions of Earth's protective ozone layer, allowing increased ultraviolet radiation to reach the surface and potentially triggering mass extinction events. Some researchers have proposed connections between nearby supernovae and historical mass extinctions, though the evidence remains controversial and highly debated. The late Ordovician extinction, approximately 450 million years ago, coincides roughly with evidence for nearby supernova activity. But establishing definitive causal relationships across such vast timescales requires extraordinary evidence that currently doesn't exist. The proposed mechanisms for supernova climate influence involve complex atmospheric chemistry rather than simple thermal heating. High-energy photons from stellar explosions could dissociate nitrogen and oxygen molecules in Earth's upper atmosphere, creating nitrogen oxides that catalytically destroy ozone. Reduced ozone protection would allow more solar ultraviolet radiation to reach Earth's surface, potentially damaging ecosystems and altering global climate patterns through complex feedback mechanisms. Isotopic evidence in geological formations sometimes preserves signatures of cosmic ray bombardment that might correlate with supernova activity. Iron-60, a radioactive isotope produced primarily in supernova explosions, has been detected in deep-sea ferromanganese crusts and ice cores, providing direct evidence that Earth occasionally experiences enhanced cosmic ray exposure from stellar sources. Iron-60 tells a story written in atomic nuclei. This radioactive isotope, with a half-life of roughly 2.6 million years, forms almost exclusively in supernova explosions. Finding it in Earth's geological record provides direct evidence that our planet has been bathed in debris from stellar explosions occurring within our cosmic neighborhood. The Iron-60 isn't left over from Earth's formation. It arrived later, deposited by supernova remnants that expanded through interstellar space and eventually reached our solar system. Scientists discovered Iron-60 in deep-sea ferromanganese crusts, mineral deposits that form extremely slowly on the ocean floor. These crusts grow at rates measured in millimeters per million years, creating natural archives of material falling from space. By analyzing different layers corresponding to different geological periods, researchers found elevated Iron-60 concentrations roughly 2 to 3 million years ago. This isotopic spike suggests Earth experienced enhanced cosmic ray exposure, possibly coinciding with supernova activity in nearby stellar associations. Antarctic ice cores provide additional evidence. These cylindrical samples, drilled from ancient ice, contain atmospheric particles trapped when snow fell thousands or millions of years ago. Analysis of ice layers reveals Iron-60 deposited during specific time periods, offering independent confirmation of the deep-sea crust findings. The convergence of multiple independent data sources strengthens confidence that these isotopic signatures reflect genuine cosmic events rather than measurement artifacts. The distances involved matter enormously. For supernova debris to reach Earth in detectable quantities, the explosion must occur relatively nearby in astronomical terms. Estimates suggest the Iron 60 signatures reflect supernovae within roughly 300 light-years, possibly from the Scorpius-Centaurus association, a region of young, massive stars that occasionally explode as they exhaust their nuclear fuel. 300 light-years sounds vast by human standards, but represents our immediate cosmic neighborhood in galactic terms. The Milky Way spans 100,000 light-years across. Supernovae occurring within a few hundred light-years are essentially next-door neighbors, close enough for their debris to eventually reach our solar system after thousands of years of expansion through interstellar space. The question of whether enhanced cosmic ray exposure actually influenced terrestrial climate, atmospheric chemistry, or biological evolution remains open and actively researched. Some theories propose connections between cosmic ray flux variations and ice age cycles, though the mechanisms remain speculative and evidence inconclusive. Cosmic rays, high-energy particles accelerated by supernova shockwaves, might influence cloud formation in Earth's atmosphere by providing condensation nuclei for water droplets. Changes in cosmic ray flux could theoretically alter cloud cover and thus global climate. However, demonstrating such connections requires showing that cosmic ray variations produce measurable climate effects larger than natural variability. Earth's climate responds to numerous factors, including solar radiation changes, volcanic activity, ocean circulation patterns, and greenhouse gas concentrations. Isolating potential cosmic ray influences from these dominant terrestrial processes presents enormous challenges. The Iron 60 detections suggest Earth experienced enhanced cosmic ray bombardment roughly 2 to 3 million years ago. This period coincides with the Pliocene-Pleistocene transition, when Earth's climate shifted toward glacial-interglacial cycling. Whether these events are causally related or merely coincidental remains unclear. Human brains evolved to detect meaningful patterns in complex environments. The rustle in tall grass that might signal a predator, the cluster of clouds that could bring needed rain, the seasonal changes that determined when to plant crops. This pattern recognition capability represents one of our species' greatest cognitive strengths, allowing our ancestors to survive in unpredictable environments by extracting order from apparent chaos. But this same neural architecture that helped humans thrive can also misfire. We detect patterns even when none exist. We perceive faces in clouds, see constellations connecting unrelated stars, and find significance in random sequences of events. Psychologists call this apophenia, the tendency to perceive meaningful connections in random or meaningless data. The phenomenon operates largely below conscious awareness. Our brains automatically scan for correlations that might indicate causation, seeking explanations for why events occur together in time or space. This automatic processing served our ancestors well when false positives carried minimal cost. Better to mistake a rustling branch for a predator and retreat unnecessarily than to ignore a genuine threat. Modern humans inherited this hair-trigger pattern detection system. We apply it to everything from stock market fluctuations to sports statistics to cosmic events. When dramatic phenomena cluster in time, twin novae, twin earthquakes, solar storms, and an interstellar visitor. All within the same week, our pattern recognition systems activate automatically. The clustering feels meaningful, significant, possibly connected through hidden mechanisms. This feeling exists independently of whether genuine physical connections exist. The subjective experience of perceiving a pattern doesn't validate the pattern's objective reality. Human history overflows with examples of apparent patterns that dissolved under careful scrutiny. Astrology seemed to reveal celestial influences on human affairs until controlled studies found no predictive power. Biorhythm theory appeared to explain performance variations until statistical analysis showed the cycles were arbitrary. The September 2025 convergence triggers this pattern recognition system powerfully. The temporal compression of events across multiple domains creates a narrative structure that feels almost scripted. 2 stars explode within days. 2 earthquakes rupture within hours. Solar storms thread through space during the same window. An interstellar visitor approaches Mars while carrying material from another stellar system. Our minds automatically search for explanations. Could space weather influence earthquakes? Might stellar explosions somehow affect Earth? Does the interstellar visitor's presence indicate something more than coincidence? These questions emerge naturally from pattern-seeking cognition, but asking them doesn't validate the connections they imply. Distinguishing genuine patterns from perceived patterns requires methods that override our intuitive pattern detection. The scientific method developed precisely to address this challenge. Controlled experiments, statistical analysis, replication studies, and peer review provide systematic ways to test whether apparent patterns reflect real relationships or cognitive artifacts. While 3i Atlas captures headlines as an interstellar visitor, October 2025 promises a second celestial spectacular that could steal the show. Comet C/2023 R2, discovered in SOHO SWAN data by amateur astronomer Vladimir Bezugi on September 11th and 12th, is racing toward its closest approach to Earth on October 20th and 21st, potentially reaching naked-eye brightness during the same weeks that 3i Atlas performs its Mars flyby. The discovery story itself demonstrates the power of citizen science in modern astronomy. SOHO, the Solar and Heliospheric Observatory, continuously monitors the Sun's corona and surrounding space environment. Its SWAN instrument, the Solar Wind Anisotropies instrument, maps hydrogen emissions throughout the heliosphere, occasionally detecting comets as they brighten and begin outgassing while approaching the inner solar system. Vladimir Bezugi, scanning through publicly available SWAN data, noticed a brightening object that didn't match any known comet or asteroid. His careful analysis of multiple images confirmed the object's cometary nature and provided preliminary orbital calculations, suggesting a long-period comet making its first recorded approach to the inner solar system in human history. Comet Swan reached perihelion, its closest approach to the Sun, on September 12, 2025, just days after its discovery. This timing explains the rapid brightening that initially caught Bezugi's attention. Comets typically brighten most dramatically as they approach perihelion, when increasing solar heating liberates volatile compounds from their nuclei and creates the characteristic coma and tail structures that make them visible from Earth. The orbital geometry favors October observations from both hemispheres, though southern observers initially enjoyed superior viewing conditions. As October progresses, the comet's position relative to Earth and the Sun improves for Northern Hemisphere observers, potentially offering excellent viewing opportunities for the largest number of amateur astronomers and casual sky watchers. Current brightness predictions suggest Comet Swan could reach magnitude 4 to 6 during its closest approach to Earth, bright enough for naked eye visibility under dark skies, though binoculars or small telescopes would reveal far more detail of its coma and tail structure. These brightness estimates carry substantial uncertainty because comet behavior remains notoriously unpredictable, especially for new comets making their first recorded approach to the inner solar system. The timing creates a perfect confluence of celestial events during late October 2025. The new moon phase around October 20th and 21st eliminates lunar interference that often washes out faint celestial objects. The annual Orionid meteor shower reaches peak activity during the same nights, created by debris from Comet Halley intersecting Earth's orbit. Sky watchers could potentially observe a bright comet, multiple meteors per hour, and the continuing evolution of 3-eye Atlas, all during the same optimal viewing sessions. Comet Swan's status as a long-period solar system comet contrasts sharply with 3-eye Atlas's interstellar origins. While both objects likely contain similar volatile compounds, water ice, carbon monoxide, carbon dioxide, and various organic molecules, they formed in entirely different environments. Perfect timing. New moon conditions eliminate lunar interference that often washes out faint celestial objects. The annual Orionid meteor shower reaches peak activity during the same nights, created by debris from Comet Halley intersecting Earth's orbit. Sky watchers could potentially observe a bright comet, multiple meteors per hour, and the continuing evolution of 3-eye Atlas, all during the same optimal viewing sessions under dark moon conditions. Wide-field cameras can capture both objects in the same frame, documenting their relative positions, brightness, and tail structures for comparison. Time-lapse photography could reveal changes in coma morphology, tail orientation, and overall brightness as solar wind conditions vary, and the object's distances from Earth and the Sun change daily. The unpredictable nature of comet brightness evolution adds excitement and uncertainty to October's viewing prospects. Some comets exceed brightness predictions dramatically, developing spectacular tails and reaching magnitudes that make them unmistakable naked-eye objects, even from light-polluted urban areas. Others disappoint, failing to brighten as expected, or fragmenting under solar heating stress in ways that diminish their visual impact. Comet Swan's short observational history makes reliable predictions particularly challenging. Unlike periodic comets that return regularly and allow astronomers to study their behavior patterns over multiple apparitions, new long-period comets like Swan offer no historical precedent for their brightness evolution, outgassing rates, or structural stability under solar heating. The potential for dramatic tail development adds visual appeal to October's comet viewing opportunities. Both dust and ion tails could become prominent features as solar wind activity continues at elevated levels during solar maximum conditions. Disconnection events, where coronal mass ejections sever ion tails from comet nuclei, might become visible in real time through telescopic observations, offering rare glimpses of space weather physics in action. Amateur comet observers employ various techniques to track brightness changes and morphological evolution. Visual magnitude estimates compare comet brightness to nearby stars of known magnitude, providing data that professional observatories cannot obtain continuously. Photographic methods using digital cameras and CCD systems provide more precise measurements, while documenting structural changes in coma and tail features. Binoculars often provide better comet viewing than telescopes for casual observers. The wide field of view shows the complete comet, nucleus, coma, and tail in context, rather than magnifying small portions that may lose the overall visual impact. 7 by 50 or 10 by 50 binoculars represent optimal choices, providing enough light-gathering power to reveal faint details while maintaining comfortable viewing angles. The convergence of 2 bright comets during October 2025 offers unprecedented opportunities for comparative observations. Side-by-side viewing could reveal differences in coma color, tail orientation, and overall morphology that reflect their different origins and evolutionary histories. Time-lapse photography, spanning several nights, could document how each object responds to changing solar wind conditions and viewing geometry. Professional observatories worldwide have coordinated observation campaigns for both objects, ensuring comprehensive coverage across multiple wavelengths of electromagnetic radiation. October 3rd, 2025 marks a pivotal moment in interstellar visitor science. 3I Atlas will pass within 0.19 astronomical units of Mars, roughly 28 to 30 million kilometers from the red planet. This close approach offers unprecedented opportunities for detailed observations using Mars orbital missions, including ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft positioned to study the visitor from a cosmic front row seat. Harvard astronomer Avi Loeb described the Mars encounter as a blind date between an interstellar visitor and our neighboring world. Mars Reconnaissance, Orbiter's high-rise camera, capable of resolving features as small as 30 centimeters on the Martian surface, should achieve pixel scales of roughly 30 kilometers when pointed toward 3I Atlas during closest approach. While this resolution won't reveal surface details of the visitor's nucleus, it may distinguish between a compact central condensation and more diffuse coma structure. The scientific value of these observations extends beyond simple imaging. Spectrographic measurements during the Mars flyby could reveal the chemical composition of gas escaping from the visitor's nucleus as solar heating liberates ancient volatile compounds. Expected spectral lines include CN cyanogen, CO carbon monoxide, and CO2 carbon dioxide, molecules that would provide direct evidence of the visitor's chemical makeup and clues about conditions in its birth stellar system. The viewing geometry offers advantages impossible to achieve from Earth-based observatories. Mars orbiters will observe 3I Atlas from positions that provide different viewing angles, potentially resolving ambiguities about the visitor's size, shape, and activity level that single viewpoint observations cannot address. Simultaneous observations from Mars and Earth could provide parallax measurements that constrain distance and physical dimensions more precisely than previous interstellar visitor encounters allowed. ExoMars Trace Gas Orbiter carries spectrometers designed to detect trace gases in the Martian atmosphere, instruments that could potentially characterize molecular emissions from 3I Atlas during closest approach. Detection of specific molecular species would provide direct evidence of the visitor's composition and how solar heating liberates volatiles from interstellar ice. Ground-based observatories worldwide continue coordinating observation campaigns through the International Astronomical Union's Minor Planet Center and various professional astronomical organizations. The goal involves comprehensive multi-wavelength monitoring that tracks brightness changes, spectroscopic evolution, and morphological variations as 3i Atlas responds to varying solar wind conditions during its inbound journey. The Mars flyby represents the first time in recorded history that an interstellar visitor will pass within range of spacecraft specifically designed to study small bodies. Unlike Oumuamua, which departed too quickly for detailed study, or Borisov, which remained relatively distant throughout its passage, 3i Atlas provides extended observation opportunities that may answer fundamental questions about interstellar material and how it differs from objects formed in our own solar system. October 29th, 2025 represents 3i Atlas's moment of maximum solar heating as it reaches perihelion at approximately 1.36 astronomical units from the Sun. This closest approach to our star will subject the interstellar visitor to thermal conditions that may liberate volatile compounds locked in its nucleus for millions of years during its journey through interstellar space. Perihelion observations could reveal whether 3i Atlas follows typical comet evolution patterns or displays unique characteristics reflecting its interstellar origins. Solar heating may produce dramatic brightness increases, spectacular tail development, or fragmentation events that distinguish interstellar visitors from solar system comets formed under different conditions. The perihelion distance keeps 3i Atlas outside Earth's orbit, farther from the Sun than our planet, but close enough for detailed ground-based observations throughout late 2025. Professional observatories worldwide have coordinated observation campaigns to monitor brightness changes, spectroscopic evolution, and morphological variations as the visitor responds to peak solar heating. The scientific questions focus on how material formed around another star behaves when subjected to our Sun's radiation and solar wind at close range. As 3i Atlas approaches perihelion, solar heating penetrates deeper into its nucleus, warming ice that has remained frozen since the object's formation billions of years ago. The sublimation process, where ice transforms directly from solid to gas without passing through liquid phase, accelerates dramatically as temperatures rise. This outgassing creates the expanding coma of gas and dust that makes comets visible from Earth. The chemical composition of this outgassing reveals information about the visitor's birth environment. Different volatile compounds sublimate at different temperatures. Water ice requires relatively warm conditions to vaporize efficiently, while more volatile species like carbon monoxide and carbon dioxide sublimate at much lower temperatures. By tracking which molecules appear in spectroscopic observations at different distances from the Sun, astronomers can map the chemical stratification within the nucleus. 3i Atlas's interstellar origins make these observations particularly valuable. Did this object form in a stellar system with different chemical abundances than our own? Has cosmic ray exposure during millions of years of interstellar travel altered its surface composition? Does it contain isotopic ratios that differ from solar system objects, providing clues about nucleosynthesis processes in other stellar neighborhoods? The visitor's activity level at perihelion will constrain models of its size and composition. Highly active comets produce large amounts of gas and dust relative to their nuclear size, while less active objects may be largely depleted of volatile compounds or covered by insulating dust layers that inhibit sublimation. Comparing 3I Atlas's perihelion behavior to solar system comets at similar distances helps determine whether interstellar and solar system objects share similar evolutionary histories or display fundamental differences. Tail development becomes most dramatic near perihelion when outgassing rates peak. Dust tails curve gracefully away from the sun, pushed by radiation pressure acting on microscopic particles. Ion tails stream straight away along magnetic field lines embedded in the solar wind. Both tail types could become prominent features in telescopic images, potentially visible through binoculars or even naked eyes, if the visitor brightens sufficiently. The potential for fragmentation adds uncertainty to perihelion predictions. Some comets break apart when thermal stress exceeds their structural strength, creating multiple fragments that gradually separate along the orbital path. While fragmentation would complicate subsequent observations, it would provide unprecedented opportunities to study the internal structure of interstellar material. December 19th marks 3I Atlas's closest approach to Earth at roughly 1.8 astronomical units, approximately 270 million kilometers. For comparison, this distance is closer than Mars at its most distant point from Earth, providing excellent viewing conditions for both professional observatories and amateur astronomers with modest telescopes throughout the winter months. The extended observability of 3I Atlas through early 2026 ensures that scientific investigations can continue long after the initial excitement of the Mars flyby and perihelion passage. Unlike Oumuamua, which departed the inner solar system too quickly for comprehensive study, this interstellar visitor offers months of detailed observation opportunities as it evolves under changing solar heating conditions and space weather influences. December observations benefit from the visitor's favorable position relative to Earth. As 3I Atlas moves outbound from perihelion, it remains well placed for Northern Hemisphere observers during evening hours. The winter sky's longer nights provide extended observation windows, particularly valuable for time series photometry that tracks brightness variations over hours or days. Professional observatories schedule deep imaging campaigns during closest approach. Large telescopes can detect faint features in the visitor's coma and tail that smaller instruments cannot resolve. Spectroscopic observations reveal which molecules are actively sublimating from the nucleus as it gradually cools while receding from the sun. Radio telescopes search for molecular emission lines that provide information about temperature structure and chemical composition within the expanding coma. Amateur astronomers contribute crucial monitoring observations that professional facilities focused on multiple targets cannot maintain continuously. Visual magnitude estimates, CCD photometry, and imaging by dedicated amateur observers provide the temporal resolution needed to detect short-term variations that might correlate with specific space weather events or rotational modulation of the nucleus. The December geometry also enables astrometric measurements that refine the visitor's orbital parameters. Precise position measurements from multiple observatories worldwide help determine whether 3I Atlas experienced any non-gravitational forces, tiny accelerations caused by outgassing that can alter trajectories in measurable ways. Such measurements constrain models of the visitor's mass, rotation state, and activity level. By December, months of observations will have accumulated, allowing researchers to characterize how 3I Atlas's behavior evolved as it approached and departed perihelion. Did brightness increase follow predicted patterns for typical comets? Or did the interstellar visitor display unique characteristics? Did spectroscopic signatures reveal unusual chemical compositions or isotopic ratios that differ from solar system objects? Did tail morphology show evidence of interactions with coronal mass ejections or other space weather phenomena? The closest approach provides optimal conditions for parallax measurements using widely separated observatories. When observers thousands of kilometers apart simultaneously image 3I Atlas, they see it from slightly different angles. This parallax, combined with precise timing, allows triangulation that determines distance more accurately than orbital calculations alone. Educational opportunities multiply during closest approach when the visitor reaches maximum brightness and accessibility for amateur equipment. Schools, astronomy clubs, and public observatories often organize special viewing events that introduce newcomers to comet science, while providing experienced observers with opportunities to study an object of fundamentally different origins than anything else in the night sky. The December observations represent the final chapter of 3I Atlas's intimate encounter with our solar system. After closest approach, the visitor will continue its outbound journey, gradually fading as it recedes toward the outer solar system, and eventually returns to interstellar space, carrying with it whatever modifications our sun's radiation and solar wind have imposed on this traveler from the stars. 3I Atlas represents far more than a curiosity from interstellar space. It's potentially the most sensitive natural probe we've ever had for studying how our sun interacts with material formed around other stars. The visitor's extended journey through the inner solar system during solar maximum conditions provides unprecedented opportunities to observe space weather effects on matter that spent millions of years wandering between stellar systems. Think of the interstellar visitor as a floating instrument package that costs nothing to build or launch. Its ion tail functions as a natural magnetometer, revealing invisible magnetic field structures embedded in the solar wind. Changes in tail brightness and morphology indicate variations in solar wind density, speed, and magnetic field orientation. Professional space weather researchers extract quantitative measurements from such observations, turning telescopic images into plasma diagnostic data. The Mars flyby on October 3rd provides viewing geometry impossible to achieve from Earth alone. Simultaneous observations from Mars orbiters and ground-based telescopes create a three-dimensional picture of how the visitor responds to local space weather conditions. If coronal mass ejections interact with 3I Atlas during this period, spacecraft at Mars and Earth observe the same event from different vantage points, constraining models of magnetic reconnection and plasma dynamics. Spectroscopic observations reveal which molecules sublimate from the nucleus under varying solar heating and space weather conditions. As 3I Atlas moves from discovery through perihelion and beyond, astronomers track how CN, CO, CO2, and other species evolve. Do production rates follow patterns established by solar system comets? Or does interstellar material respond differently to solar radiation? The visitor's chemical composition carries information about its birth stellar system. Stars with different masses and evolutionary histories produce different patterns of heavy element abundances through nucleosynthesis. If 3I Atlas shows isotopic ratios that differ from solar system norms, This reveals conditions in the molecular cloud where it formed billions of years ago. Professional observatories employ multiple techniques to extract maximum information from limited photons. High-resolution spectroscopy resolves individual molecular emission lines, revealing Doppler shifts that indicate expansion velocities within the coma. Polarimetry measures how dust particles scatter sunlight, constraining grain sizes and compositions. Radio observations detect molecular transitions that occur only at specific densities and temperatures, mapping physical conditions within the expanding gas cloud. Amateur contributions remain essential despite sophisticated professional capabilities. Continuous monitoring by dedicated amateur observers provides temporal coverage that snapshot observations from major telescopes cannot achieve. When 3I Atlas brightens suddenly or displays morphological changes, amateur networks often detect these variations first, alerting professional facilities to schedule follow-up observations. The extended observation window through early 2026 allows long-term studies impossible for previous interstellar visitors. Researchers can track how the visitor's activity evolves as solar heating increases toward perihelion, then decreases during outbound travel. Does 3I Atlas follow the symmetric brightness curve typical of many comets? Or does it show asymmetries that indicate subsurface heat storage or seasonal effects from nucleus rotation? The space weather context adds another dimension to these observations. Solar cycle 25 maximum conditions mean 3I Atlas experiences more coronal mass ejections, solar flares, and high-speed solar wind streams than previous interstellar visitors encountered. Each interaction provides data about how our sun's magnetic field couples to interstellar material. Step back for a moment and consider what we've mapped across these chapters. Twin stellar explosions visible to the naked eye. Twin magnitude 6 earthquakes rupturing within hours of each other. Coronal mass ejections threading through the inner solar system, and an interstellar visitor crossing our neighborhood during solar maximum conditions. A lot of universe happening very fast, compressed into late September 2025. Each phenomenon follows well understood natural laws operating independently. Stellar physics explains novae as thermonuclear runaway on white dwarf surfaces. When accumulated, hydrogen reaches critical temperature and pressure. V 1935. Centauri and V 7994 Sagittarius represent normal examples of binary star evolution. Spectacular to observe, but predictable in mechanism. Plate tectonics explains the Venezuelan earthquakes through stress accumulation and sudden release along the Caribbean-South American plate boundary. The magnitude 6.2 and 6.3 events followed established patterns of main shock and aftershock sequences. Stress transfer between adjacent fault segments explains why the second rupture occurred 5.5 hours after the first. Regional geology and historical seismicity place these events within expected ranges for this tectonically active zone. Solar physics explains coronal mass ejections as consequences of magnetic field evolution during solar maximum. The Sun's 11-year activity cycle reached peak conditions during 2025, making elevated space weather statistically expected rather than anomalous. The Russell-McFerran effect during autumn equinox provided additional geometric enhancement that amplified whatever space weather occurred. Orbital mechanics explains 3I Atlas's trajectory through the inner solar system. The interstellar visitor follows hyperbolic orbit determined by its velocity and direction, when entering our stellar neighborhood millions of years ago. Its approach during solar maximum and favorable viewing geometry represent fortunate timing for observations, but reflect no deeper connection to terrestrial or stellar events. The scientific mainstream maintains clear positions on potential connections between these phenomena. The United States Geological Survey states that no demonstrated physical mechanism links space weather to earthquake occurrence. Decades of correlation studies failed to establish reliable predictive relationships, while some researchers continue exploring subtle electromagnetic or gravitational coupling mechanisms. Proposed effects remain orders of magnitude too small to influence earthquakes meaningfully. Yet, acknowledging mainstream scientific positions doesn't require dismissing the remarkable nature of this temporal cluster. Sometimes, the universe arranges itself in ways that compress multiple dramatic events into brief windows. The clustering feels significant because human pattern recognition evolved to detect meaningful correlations. This cognitive capability served our ancestors well, but can also perceive significance in coincidental timing. The most scientifically honest assessment separates observed facts from speculative connections. Twin novae occurred at distances measured in thousands of light years. Twin earthquakes released energy accumulated over decades of tectonic stress. Solar storms propagated through space following electromagnetic physics. An interstellar visitor traversed the inner solar system on a trajectory determined millions of years ago. These events shared temporal proximity, but operated through independent physical mechanisms. The convergence represents a data point in cosmic history, remarkable for its compression of phenomena across multiple domains, but explainable through established science operating on familiar timescales. Whether future observations reveal subtle connections currently unknown, or confirm that September 2025 simply clustered unrelated events, remains to be determined through continued investigation.